Okay, so last time we discussed that the continuous problem, our model problem, at least our model problem, the Poisson equation with, but also more general elliptic equations, fulfill maximum principles. There are various ranges of maximum principle. There's the notion of the weak maximum principle saying that the maximum under certain conditions is attained at the boundary. And there's the strong maximum principle saying if the maximum is attained, the maximum on the closure is attained in an interior point, then the solution has to be constant. In this sense, I was a little bit confused last time. In this sense, this formulation is correct. We talk about the maximum. It's here now in the discrete case about the maximum at the points, the grid points in the interior and at the boundary, with the exception of those points which do not interact with anything. And in the situation, that is the claim in the situation that the maximum is attained at an interior node, at an interior grid point, then the solution has to be constant. And an immediate consequence of this is, from the strong maximum principle, is the weak maximum principle, also in the discrete setting, saying that the maximum on the set of the interior grid points is less or equal the maximum on the set including the boundary grid points. Okay. Sorry, no, that's also correct. That's a trivial statement on the set of the boundary grid points. Okay, so let's go through the proof. I have the proof here on the transparency. I think we don't have to write it on the blackboard. It's quite easy to comprehend. And here we will see which properties of the discretization matrix AH will enter. And this we will formalize in the sense that we will then, in the next step, speak about sets of equations, that is, discretizations of differential equations, not necessarily in 2 dimensions, not necessarily only with Dirichlet boundary conditions, which have these properties, and see what we can do with these properties. So in a second there will come a long list of conditions, and it will be helpful for you if you have some material where you can have a look at this list of conditions that you can, if I then refer to number 5 or 6 or something, you can have a look at it. That I'm not obliged to go back and forth all the time. So let's start here with the proof. Still in our model case, rectangle, 5-point stencil, Poisson equation. So we have the value, the maximal value here attained at this point. We call this value u bar. And then we look at the corresponding stencil, where this u bar is in the center. As the right-hand side, so the equation is then for, if I omit the 1 over h square, so I multiply through by this factor, the equation is then 4u star minus all the neighbors, the values at all the neighbors, the 4 neighbors or maximal 4 neighbors which appear in the stencil, equals the right-hand side. As the right-hand side is less or equal to 0, that is a very important assumption here, we can write this in this inequality just by estimating the f by 0 from above. So we have this inequality here just by the assumption, just by the way how the stencil looks, and by the assumption f equals to f less or equal to 0. And this is just the fact that we have at least 4 neighbors, and of course UH is the maximum, and each of these individual values can be estimated by UH. So we now have an inequality which starts and ends with the same number, so it has to be an equality. But as we have here estimated each member of the sum individually by u bar, we also have to have the equality UH at this grid point has to be u bar. So the consequence of this consideration is that on all the neighboring points, on all the at most 4 neighboring points, the solution has to be constant, equals the maximal value u bar. And now we iterate on this argument. Now we go to one of these neighbors, look at the stencil there. That means look at the neighbors of the neighbors and go on. And the fact that, and I hope you have discussed this already, or will do this soon, the fact that we have assumed that the matrix is irreducible is equivalent with the fact that doing so, we can go from every nodal point, from every grid point to every grid point. So after a finite number of steps, we will have shown that the solution is constant equals u bar at every grid point. And in particular also the Dirichlet boundary points which we reach by that. And so we have shown the assertions. The only exceptional points are those 4 corner points in this specific example because they do not appear in any stencil. Therefore, we have to take them out. They are sort of an artifact in this method. It doesn't matter which values we prescribe here because these values do not enter in the discrete in the definition of the discrete problem. Okay, so that is what I basically said, what's written here down in words. And now we want to try to, as I said already, to generalize this situation. So we now look, we could even write it down even a little bit more formally, at least formally more general, but I decided to keep the notation as close as possible to the specific situation, that you can always refer to the specific situation. So we now look at a general set of equations with a matrix AH in a certain amount of degrees of freedom. Up till now, these were the inner nodes. If in the case where we have additionally Neumann or flux or mixed boundary conditions, those nodes will, as we have seen already in discussing the corresponding discretizations, those nodes will also go into this set, and the remaining set, where the corresponding amount is denoted by M2, these are the remaining Dirichlet nodes. So the assumption always is that we have at least some part where we have Dirichlet conditions, or something like that. And we discussed this already. There's also a background. The pure Neumann problem has no unique solution. So to include the pure Neumann problem into the theory, which is also possible, we have to make a few changes. So we have then this right-hand side. This right-hand side consists of the discrete approximation of the right-hand side of the PDE, which may be the evaluation or maybe something also otherwise H-dependent, as we said, which now not explicitly given here in the notation, but of course is also H-dependent, even is the evaluation of the exact right-hand side at the grid, because the grid is changing. And here we have, so to speak, the influence of the fixed, of given boundary data, so basically the Dirichlet data, and we have seen this matrix minus AH hat is, so to speak, the half of the discretization matrix of the matrix coming from the stencils put to the right-hand side because of as the values are known here. So this structure we assume. And now we need some assumptions on these ingredients we have there. And and we just take the same properties we have seen from our model problem. Before doing that, let's do some further notation. So, so M, if I speak of M, this is just the sum of all grid points. And if I put the matrices together, AH and AH hat, then I call this matrix AH tilde. This is now a rectangular matrix as AH hat is a rectangular matrix. It has as many rows, so to speak, that means conditions in the equations, as we have unknowns to solve for, but it has the full amount of numbers of the nodal points. And always keep in mind, we are not interested in on a fixed dimensional situation, M or M1 or M2 or H. We are always considered in the situation H going to 0. So we are looking at an individual finite dimensional problem, but this is only a member of a family where then the dimension goes to infinity. Okay, now let's have a look at the properties which we have seen in our model case, and we will assume then these this is here numbered, I think, in the German version with 128, I think in the English version with 132, and I will refer to those properties, to those 7 properties, and to variants of these 7 properties in the following several times. So what do we have? The diagonal elements, so first we speak about the matrix AH. The diagonal elements are positive. The off-diagonal elements are non-positive, and the sum of the entries is greater or equal to 0. And at least for one index, for one row, we have a strict inequality here. As we have these sign conditions, we can write these conditions equivalently as AHRR, the modulus of the diagonal element, is greater or equal the sum of the moduli of the off-diagonal elements. That is what is called diagonally dominant or weakly diagonally dominant. The notation change is a little bit not so well defined what is really diagonally dominant and strictly diagonally dominant, but in any case, at least these 2 conditions to sum, and this is then at least diagonally dominant here. Okay, then we have seen our example is irreducible. We will discuss this property in a second a little bit. And now we come to the, so to speak, right-hand side, to the additional equation, to the treatment of the Dirichlet boundary conditions. And here we assume that all the entries of AH hat are less or equal to 0, because they come from this off-diagonal elements of the stencil. As they appear on the right-hand side with a minus, this means that the matrix in front of the UH is a matrix with non-negative entries, what we call a positive matrix or a monotone matrix. That means, okay, what that means we'll discuss in a second. Then we have the condition that the sum of the full rows is greater or equal to 0, and then this is a sort of a technical assumption saying we do not have involved Dirichlet data which have no influence at the solution whatsoever. It says if we look at any column here in this right-hand side in the AH hat matrix, that means at any Dirichlet point, then this Dirichlet point must at least play a role in one of the equations. Otherwise, it's clear. What we want to show at the end of the day, or not at the end of the day, pretty soon, I hope, is that we have a monotone dependence of the solution on the data. What that means, I will make clear in a second. And of course, for that reason, we of course need that the real data really acts into the solution. Otherwise, of course, I can't do anything with the data. Okay, so the notation we had, we just now generalized to this situation. We have spoken of neighbors oriented by the entries in the stencil, and we do the same thing if we have an index S. That means a row in the system. We call all the indices a part of, an index R. We call all the S different from R neighbors if the corresponding entry in the row is not equal to 0. These are the neighbors, correspondingly to the definition what we had. And I said this already, as a consequence of the irreducibility means that I can connect any 2 points which are in this collection 1 to M1 by a relationship where always one is the neighbor to the other. Or if I look at the adjacency graph, who knows this word, adjacency graph? Okay, you will know this after this special tutorial about irreducible matrices. It just means the adjacency graph is connected. You can go from each node to the other. Okay. What we should keep in mind is that is a redundant formulation. It's not formulated in a way that we write down minimal conditions, but to have it quite handy. You see, by this condition here and by this condition, I can conclude this condition here, for example. Okay, I think I have said everything. And now I said already we want to, the way we want to deal with the problem, also theoretically, with the final aim to show stability in the L infinity norm is to go via monotonicity relationships. So what we do is we use a partial ordering both on the vectors and on the matrices, which you might have seen already, hopefully. So we define that a vector is greater or equal than the zero vector if this holds true for all the components. If we have defined what it means that a vector is greater or equal to 0, we can define what it means that a vector is greater or equal to another vector v just by saying that u minus v must be greater or equal to 0. That immediately implies that this partial ordering is compatible with the summation of our vector space as we are used to in R, for example. With the matrices, we do exactly the same thing. So in this sense, matrices are just strangely written down vectors, long vectors. So we denote what so we have the notion that a matrix is greater or equal to 0 or positive. Of course, more precisely, one should say non-negative, but I will say positive. In this notation, what we have seen is that the matrix in front of the UH hat values of the fixed Dirichlet values on the right-hand side is just a positive matrix. That was the assumption. Okay, if we have a positive matrix, then of course the linear mapping becomes a monotone mapping in the sense if I have that a matrix A is positive, and you should keep in mind that there's another partial ordering on the matrices which also makes sense. What do I mean? Which other partial ordering you know, at least for symmetric matrices? Usually this notation, therefore one has to be a little bit careful when writing down this notation, but obviously you do not connect any other notion with this notation, so we don't have a problem. So what other partial ordering we have on the symmetric matrices? A partial ordering in the sense that it induces an order relation which is compatible in the usual sense with the algebraic structure. Positive semi-definiteness. So often one uses also this notation to denote a positive semi-definite matrix. This I do not use here. In this sense, I use it in this pointwise sense as I just explained. So if we have a positive matrix, if we have a vector x less or equal to y, and then we ask ourselves, what is the relation between these two vectors? Do we know anything about the relation between these two vectors? What do I have to write in the middle? Or is it not clear? Less or equal, yeah. This is similar to multiplying with a non-negative number in the reals. So, and this is a relation we will use in a little bit different setting, but keep this in mind. And of course, this makes clear that we need something. I said we want to have monotonicity of the solution in the. Let's go back for a second, that we know already what we would like to know. So I said what we would like to have, we would like to have monotonicity in the solution. We would like to have, if we have two sets of data, f1, f2, UH hat 1, UH hat 2. We have a corresponding ordering in this set of data. We want to have the same ordering in the solutions. And that is clear that we then need a monotonicity at least in this term here. And therefore, this assumption that the minus UH hat is positive is a sort of for this line of thought a necessary requirement. If we go on with this consideration, what would you expect what we need if we then want to do this final step? That we do not only want to have a partial ordering on the right-hand side, this we then have assured, but we want to bring over this partial ordering to the solutions. Which quantity should be monotone then? How do you compute the UH from the right-hand side? AH inverse. So what we would like to know is the positivity of the AH inverse. The problem is, of course, we don't have it explicitly. So we have to have conditions which assure us that all the entries of the inverse matrix are non-negative. Okay, so let's first see, go on with these conditions, and let's see that this really works. In the sense, we have first we have again a strong maximum principle, and as a consequence of this, a weak maximum principle. And and keep in mind that the assumptions we did for our discretization matrix also allows that we have a term in the equation. It's not just a Laplacian or not just an equation with second derivative or maybe first derivative. We could also allow for a zero-order term, as long as, for example, the coefficient is positive. Then we discretize this just by a, so to speak, one-point stencil. That would be most reasonable, or something different. With non-negative entries in the stencil, they would add up. Let's say a one-point stencil, they would just add up at the diagonal and would not change the properties, would just enlarge the value at the diagonal. But we have seen that in the continuous level, that in this situation, we have to have some restrictions on the maximum principle. We have to speak about non-negative maxima there. And that comes over here. So we now consider this general problem under the assumptions we discussed. Again, we assume that the right-hand side is less or equal to 0. We consider the vector consisting of the unknowns and of the known data. This is now correspondingly called UH tilde, and assume that in all these values there is a non-negative maximum, and this maximum is attained at an interior point. And the assertion is, under these conditions, this vector has to be constant. All the components have to be the same. And as an immediate consequence of this, we have that the maximum over all values is less or equal, and now we have this weakened form here of the maximum of 0. This is due to this condition here with the non-negative maximum. 0 and the maximum at the nodal points, at the boundary nodal points. So let's prove this strong maximum principle and see how the properties of the matrix we have formulated enter here. So we do exactly the same as in the special proof for the 5-point stencil. So we note the maximum of all those values with u bar, and we look for an index r belonging to the interior grid points such that there this maximum is attained. We look at the corresponding line, and as the right-hand side is less or equal to 0, we can make, out of the equality, we can make an inequality. This is given here, and here we still include all the Dirichlet points. Here the large matrix AH tilde and the long vector UH tilde appears, but of course we only have to sum about the neighbors, because otherwise by definition, those entries here are 0. By the sign condition, we can minus this entry of the matrix as the modulus of the entry. Now we have factors which are greater than or equal to 0. And now we can estimate, if we now estimate the UH tilde from above, this goes through to the product and then to the sum. And of course, we estimate those values by the maximum here. And we are here. Okay, so this is now a common factor in all those sums. And that is now, again, this diagonally dominant condition of the matrix, that we can estimate all the sum about the moduli by the value at the diagonal. Okay, now we are exactly in the same situation as we were before. We have here equality. All the inequalities become equality. All the estimates we did here and here also were valid component-wise. So we also have equality component-wise. And that means that here, of course, we have to use that this factor is non-zero here to conclude that it also holds true component-wise, but that's a definition of the neighboring points, that it's non-zero. And as a consequence, we have that the solution is constant at all the neighboring points. And now, due to irreducibility, we extend this going to the neighbors and so on. Okay. Now we want to change a little bit the assumptions. That is now not really of importance for dealing with elliptic problems, but is of importance for dealing with parabolic problems. Now, of course, we have not yet seen anything about parabolic problems, but I give you a very brief indication about parabolic time-dependent problems that you see that there the assumption of irreducibility is too strong. Let's have a look at a 1D parabolic problem. That is then called an initial. As in the ODE case, we've discussed this boundary, and of course, we are in the spatial situation, initial and boundary value problem. 1D means I have here an interval, let's say AB or 0B, 0A, doesn't matter. And here we have our time axis, and here our final time t. That is, we have a sort of a space-time domain where we want to compute the solution. And all the methods we will discuss, or the simple methods we will discuss, they work like that. We do here some time discretization. So we have here certain layers, time layers. We have a time derivative in the equation. Of course, you can expect what we do with this time derivative is substituted by a difference quotient. The consequence of this is that the situation is here initially for t0, in this case equal to 0, the solution is known, of course, by the initial data. And then the next step is having this known solution, compute U1, being the spatially distributed solution for this fixed time. Having U1, compute U2, and so on. Now, if we write this all in a big matrix, and we write this as a set of equations for all these unknowns in space and time, what do you think? Is this matrix irreducible or is it reducible? Do we have the situation as in the irreducible system that, so to speak, every unknown depends on every unknown, or do we have the situation that they separate in blocks where one block is not dependent on the others, but the others are dependent on the one? Do you see the situation here? Yeah. That is here the case, yes. Of course, the U1 is dependent on the 0, but not on the U2. It's no back to the future. Even we had this day now, but that's not Back to the Future here. That means in this situation the matrix is not irreducible. And that makes sense to have a little bit of a weaker assumption. And this, to deal once for all with this theory, I do this introduction of this weaker assumption now. To do this, I have to strengthen one of the requirements. So I have to strengthen one requirement and I weaken one requirement. I strengthen requirement 6 to 6 star, saying that the sum in the large matrix, including the Dirichlet boundary values, in the large matrix, all the row sums have to be 0, which is the case for all our stencils, and which basically reflects that a stencil is precise for a certain low-order polynomial. You can think about that. So that's a very natural assumption. And then we can weaken this this requirement of irreducibility, which said we can connect every point to every point. We only have to connect now special points with special points. And what we would like to have is we would, in the situation which may produce problems, in the situation where the sums over the square matrix AH is 0. That would refer to those nodal points where we don't have any Dirichlet boundary data involved. Nothing is, so to speak, removed from the stencil. Those points we would like to connect in the way we did it up to now, by a neighboring relation, to a point, to at least one point where we still have a positive point. So we want to connect a point which is, so to speak, far from the Dirichlet boundary to a point which is close to the Dirichlet boundary. That is the weakening of the assumption. Okay. And so in this sense, if we now speak of points far to the boundary and close to the boundary, we have to modify this notation and say we mean by this far and close to the Dirichlet part of the boundary. So, and under these assumptions now, and you see what we do now here, with this assumption, we have excluded this reaction term. We have excluded this alpha or A times U term, because then we would have, so to speak, in the discretization, a value which is not balanced by off-diagonal values. And now, of course, we can again rely or hope that we get the stronger form of the maximum principle, and this is true in the sense that, again, under these modified assumptions, if the right-hand side is less or equal to 0, we can conclude that the maximum over, there's only a weak maximum principle now, the maximum over all points is less or equal than the maximum over the Dirichlet boundary points. Let's go back in the proof and see how we have to modify here the argument. Okay. So the first observation is here this inequality becomes an equality by the strengthening of the assumption, what was it, 6 to 6 star. Because of this, we don't have to have this becomes an equality. No, sorry. This here becomes an equality. This becomes an equality. Here we use this sum property for the H tilde matrix. And because of this, we don't need a sign condition on the U prime in this estimate. So we can do this argument for every maximum, not only for non-negative maxima. This shows that we can, so to speak, improve the estimate a little bit. And what does that mean? This restricted connectivity property just means that we can, so to speak, define a way. So In each neighboring relation, we have then this constant value. And if we can go on with another neighboring relation, this constancy property is enlarged to this larger set. And this reduced requirement substitutes in the irreducibility says we can at least go from a point. So we are either close to the boundary in any case, then of course we have a neighboring point which is at the boundary, or we are far from the boundary and then we can connect to a point close to the boundary. And in this sense we come back again to this property here. Okay, now we want to take advantage of these properties, and I said we want to show that is what is called a comparison principle. It means I have solutions for the corresponding problem that is the same thing exists also in the continuous case. So we can equally well conclude comparison principle for the PDEs, for the boundary value problems based on the maximum principles there. It's always the same argument. So we have solutions UH1, UH2 for two different sets of data, F1, UH1 hat, and correspondingly with the index 2. These sets are ordered, F1 less or equal F2, UH1 hat less or equal UH2, and then the assertion is the solutions fulfill the same ordering. Now, how do we do this? We take advantage of the linearity of the problem. That is quite important here. So we just take the difference of the whole thing, and the difference of the solution is then a solution of a problem for the difference of the Dirichlet data and the difference of the right-hand side. Okay, now let's hear. The difference of the right-hand side, this is now, so to speak, our f. This is less or equal to 0 by assumption. That means we can apply our maximum principle. The maximum principle tells us the maximum is less or equal than the maximum in the weakest form 0 and the maximum at the boundary, or only the maximum at the boundary. But what is the maximum at the boundary? What do we know about? These are now the boundary condition. What do we know about the maximum at the boundary? This is the boundary conditions, and that is the assumption on these functions. Yeah, obviously all these functions are this function is less or equal to 0 always in every nodal point, and therefore of course the maximum is less or equal to 0. And if we maybe take again the maximum with 0, it's also less or equal to 0. So in any case we have less or equal to 0. That means we have the maximum over the difference of the solutions in each of the interior points is less or equal to 0. That means we have the ordering here. And you see that's just a general argument you can always do. If you have a maximum principle, you can include a comparison principle. What about, now if I have such a comparison principle, can it be that the matrix AH is singular? Is this possible? Or can we immediately conclude that in this situation the matrix AH must be non-singular, regular? How is this? We have a square matrix. What are sufficient conditions for a square matrix to be regular? In the square matrix situation, the situation of an endomorphism between vector spaces of equal finite dimension, life becomes very easy. What do I mean by this? Give me just one. There are a dozen or 2 dozens of sufficient conditions, but I'm satisfied with one. The weakest you can think of course. How would you check in such a situation whether you have? This is a reasonable question, isn't it, that a matrix is her?
The rank of the matrix size.
Okay, you would look at the rank.
Because if I want to calculate the determinant,
Yeah, okay.
I know the rank.
Okay. Can you make it a little bit more weaker? So the rank should be n if we have an n-dimensional, n by n dimensional matrix. What does that mean? So, for example, for the how do you check that the rank is n without computing it? So we're talking about a mapping, and this mapping, let's do it a little bit more in structural mathematics. So we have a linear mapping. We want to have this mapping to be bijective. So this mapping has to be injective and surjective. In principle, of course, all situations are possible, even for linear mappings, but not for linear mappings in this situation between vector spaces of the same finite dimension. In this situation, an injective mapping has to be surjective and vice versa. So we can rely on one of these properties. So what would be how do you check that the mapping is injective? The kernel is the zero space, yes. Okay. But then I have to again solve sets of equations. I just want to look at something, at the rows or the columns. Decide what you look at. Do you look at the rows or do you look at the columns? Concerning the injectivity. Yeah, not really have a good working knowledge of linear algebra, I'm afraid. What did you learn in linear algebra? This thing is absolutely trivial. More than trivial. Okay, what is this here? How do you compute this quantity? If I write a matrix, let me write a matrix first, and then I have given you already the answer. I write the matrix here in terms of its columns. So I just write one column with these are vectors here. What is this here? What is the definition of matrix times vector? Now you have to answer, because otherwise I have to ask you what 1 plus 1 is. That's the only level I can below. What is A times X? Use this notation here. What is this, yes? Yes, of course. That is the definition. That's the only sensible definition of matrix times vector is matrix times vector is the linear combination of the columns. Point. Forget all the other rubbish you have learned. So, of course, now, what means linear injectivity? What means zero kernel now in this notion? What is this? What kind of a requirement is this for this rows here? For the columns here. What do they have to have? Of course, of course.
How do you check this without solving the...
No, okay, so this is just an equivalency of notions. So, okay, you said correctly A is injective. This has nothing to do with, this is now independent of the dimensions. It's also for a rectangular matrix. You said the kernel has to be 0. What does that mean? You said if I have a solution in the kernel, it has to be 0. Okay? And I said, what does that mean? If I have a linear combination of the columns, if I have such a linear relation, it can only be the trivial relation. That means this is, so to speak, the test for linear independency. the columns have to be linear independent, or said differently, the column rank has to be maximal. For a square matrix, it doesn't make sense to say the rank is maximal. What means maximal? It can either be n or m. In the squares, in the rectangular situation. The rectangular situation, you have to specify about the column rank. So injectivity is maximal column rank, and surjectivity is maximal row rank. But in the square situation, this all comes together. Okay, so what did we see? We just have to check the injectivity, the uniqueness of the solution. Is it possible that a problem of this type has several solutions? Assume you have two solutions. Forget about all this fancy right-hand side, make the u hats to 0, just take the f's or whatsoever. Assume you have one right-hand side, f, and you have two solutions, u1 and u2, different from each other. Is this possible? No, why not? What?
Either it is a unique solution or we have...
Why is there a unique solution? Why? Prove it to me on the basis of this property. That is the question. Why is there a unique solution? So the statement is, the assertion is, if I have a comparison principle, then I also have uniqueness of the solution. And by our discussion, we have seen that also means that the corresponding matrix, being a square matrix, that's of course important, is regular. So why we have so we assume that we have two solutions. That assume we have u1, u2 being solutions for the same. I reduce now a little bit the notation to make it shorter. Being the same solutions, being the two solutions for the same data. How can I conclude then that u1 is equal u2? How do I do this on the basis of this theorem? What about this here? Is this correct? By my definition? Yes? What is the conclusion? By the comparison principle? Yeah, I guess u1 less or equal than u2. Is this correct? What is the conclusion? Okay, it's as simple as this. So, when we have a comparison principle, we know quite a bit about the problem. We know the solution is unique, and the corresponding matrix is regular. Always speaking about square matrices, the matrix is regular. One can, for us, this doesn't play any difference because of this regularity of the matrix, we are always sure if we have any right-hand side, any vector on the right-hand side, we have a now unique solution of the problem. In the PDE case, this is different. In the PDE case, it's not so clear whether you have a solution or might only have solutions for specific data or whatsoever. Therefore, there's a variant of this result, and I only write it down here for the discrete case, but you can then see how it can think about how it transfers maybe also to the PDE case. And that's a new definition and I define, let's say, UH bar. Bar has nothing to do with vector bar or so, and I call this a super solution. So the problem, I restrict a little bit the notation. The problem I write as here, UH U equals F, or UH equals FH, doesn't matter. And we call it a super solution, auf Deutsch Oberlösung, if not the problem is fulfilled, but a corresponding inequality is fulfilled. And you can imagine that for a PDE problem, it's much easier to find super solutions than solutions. And okay, then we define the notion of a subsolution, Unterlösung. And here correspondingly with less or equal to the right-hand side. And if you go through our proof, you will see we can equally well prove that we say we have a super solution, we have a subsolution, and then we can conclude, as the notation indicates, of course, that the subsolution is less or equal than the super solution. And of course, a solution is both a sub and a super solution, so it can act as both. And on basis of this, you can again do this uniqueness result as here. Okay, let's go on. We said already that this might have, we said already that this comparison principle should be related to the positivity, not of the matrix AH, but of the matrix of the inverse. Now we know that the inverse exists, and that's really the fact, because what we now can do, we can, and therefore we need only a few of the requirements. I skip a little bit the details now, because we're now talking only about the matrix and the right-hand side, and not so much the influence of the Dirichlet data. And the statement is, under those assumptions, what we have, if that's, so to speak, a special case of this here, namely the special case of subsolution equals to 0. Subsolution is not only a 0, of course, is not only a subsolution, but also a solution. Sorry, the 0 is a subsolution. Okay, I start again. If I have this assumption here, AH, greater or equal to 0, I can say I have here a right-hand side, exactly what is given here, and this right-hand side is greater or equal to 0. If this is my problem, then a subsolution is given by 0, because if I compute UH of 0, I have a 0, and 0 is less than my right-hand, less or equal than my right-hand side. And then I have the ordering solution greater or equal than subsolution. And this again, and here again, if you want, from this statement, we can conclude the injectivity and so on, what we did already. And another way to write this, so here's the statement. Another way to write this is, if I have a vector with this greater than or equal to 0, then AH to the minus 1 of this vector is greater than or equal to 0. That is exactly what we already conjectured, that this just means that the inverse matrix only has non-negative entries, is a positive matrix. And if a matrix has this property, that is, inverse matrix has non-negative entries, is a positive matrix, we call such a matrix AH an inverse positive or inverse monotone matrix, inverse monotone. And what we are doing here, we are dealing here with special, it's quite special, but very important, inverse monotone matrices, namely with those which fulfill these requirements 1 and 2, saying the diagonal entry is positive and the off-diagonal entries are non-positive. And this class of matrices is called M-matrix. Deutsch M-Matrizen. This is a very important class of matrices. In some sense, it generalizes the notion of positive definiteness to non-symmetric matrices. There are, I think, around 50 different equivalent definitions of M matrices. Okay, and now, so what we have now, we have conditions. You can put it in this way. We have now found conditions which, under the assumption of these two requirements, 1 and 2, if you only have to use these two requirements, one also sometimes speaks of a set matrix, but set like sorrow. But you don't have to use this notation. So we have M matrices in our discretization. What can we conclude from this fact? That is now the point. We still want to come up to stability. And to do so, this is what we're going to do now. And for this, we use this vector here. This is a notation. This bold 1 is the vector which has 1s at each component. Okay, and then I can see the following thing. Okay. I'm not really 100% now discuss which requirements we need. We can, but it's basically this reduced version we had discussed. So what do we want to have at the end of the day? At the end of the day, we want to see stability. Stability means an estimate for the infinity norm of the inverse of the discretization matrix. And this theorem assures such an estimate, namely by the infinity norm of a certain vector we are going to construct. Of course, this vector is H-dependent. If we can assure that the norm of this vector, of this family of vectors in H, is bounded in H, then we have our stability estimate here. So what are the requirements on this vector? Okay, we do it first a little bit more detailed and come a little bit more to a more detailed estimate, namely a stability estimate which involves directly the influence of the L infinity norm of the F and the L infinity norm of the U hat. Why is this a stability estimate? We are in a linear problem. Stability means I have different sets of data. I want to relate the difference of the solutions to the difference of the data. But as we have seen already at some place, just by differencing, we can reduce these situations and looking, so to speak, at one set of data. In the linear setting, we can shift everything to 0, so to speak. Therefore, such a statement is sufficient. And it says, I can estimate the infinity norm of the solution by the infinity norm of the distributed data times some factor. This factor is the infinity norm of a special vector, and correspondingly here for the Dirichlet data. And this estimate, again, we conclude from the above estimate, which is stronger than this estimate too. So let's see, we going here always back in generality. If we would have the 2, we forget about the second part, and we see immediately this here. Because the UH is then nothing but the AH to the minus 1 of the F, and then it's exactly this estimate here. This factor is the best constant, the minimal possible constant in such an estimate, and this then says this number is such a constant, therefore the minimal constant has to be less or equal than. That is the definition of the induced norm. Okay, so this norm estimate, and this will become important also later on, this norm estimate we can get by a more refined pointwise estimate. if we estimate, this of course means that we estimate the modulus of each of the entries, maximum norm here. This means for each of the entries, the modulus is estimated by this number. So we have to have an estimate which says for each entry, the UH can be estimated from above by this number and from below by this number. This estimate says a little bit more. It says it can be estimated from above by this number we want to have here, and here the whole function UH1 appears. Of course, the UH1 again can be estimated from above by its maximum norm, and then we're exactly at this place. But it might well be that the UH1 varies, and at some places it's smaller than in others, and this effect we lose by going to the maximum norm. So this is a stronger estimate here, including, so to speak, that's again a comparison principle, so to speak. We show an inclusion, eine Einschließung, an inclusion of the solution into two functions composed of the data and on the basis of two vectors, UH1 and UH2. Now, where are these vectors coming from? That is the definition of the vector. So there's only an inequality requirement. So there's a lot of degree of freedom in finding those vectors. And we want to have that the UH1 vector satisfies this inequality relation and the UH2 vector satisfies this inequality relation. Okay, this is the statement. So by this discussion, the only thing what we still have to prove is if we have vectors of this type, then the inequality 1 holds true. The others we have already proved. Okay, so this is quite simple now on basis of the comparison principle. So the only thing what we have to remind is that we have this inclusion here of f. That means you always have to think of this component-wise. That is how this partial ordering is defined. F can be estimated from above by the maximal norm by the 1 vector. It's just that at each component we have the inclusion to the above by the norm and to the below by minus the norm. That is what is written down here. Now we, so to speak, define a vector on the basis. The same, of course, for the UH hat. Now we define a vector VH, which is just the quantity from which we have. It's so to speak the difference in this inequality. So our assertion is this vector VH is greater or equal to 0. How can we show that VH is greater or equal to 0? We have inverse monotonicity. We just have to show that AH applied to this vector is greater or equal to 0. So let's do that. What do we get? For the first quantity, we get this. This is, so to speak, the definition of this vector. We have here a non-negative factor. This preserves the inequality. Of course, we would not be allowed to multiply here with a negative number. And this is just by the same thing applies to this term and this here. And the other two parts, this and this, just comes from the fact that UH fulfills the equation. Now let's look at the sign. This quantity is greater or equal to 0. This quantity is greater or equal to 0. Now we multiply by a positive matrix. That is basically this statement here with x equals to 0. Now we multiply with a positive matrix minus AH hat. Then the whole thing is also non-negative. The sum is then non-negative and we are done here. And the rest, the other inequality, we do exactly the same. So we have now this inclusion. Vielleicht sollte man ein bisschen abdunkeln. Wird immer heller hier. Hilft das was? Okay, so we now have this inclusion now. And okay. And on the basis of this inclusion, we have seen we are not yet at stability. So, but we now know what we have to do to show stability. We have to construct vectors of this type here such that we can estimate those quantities by one number independent of h. So let's do this first. So that is what's stated here. Let's do this first for the 5-point stencil on the rectangle. And then okay, so what we do is look at these two functions, w1 and w2. And these are two polynomials, obviously. Parabolas opened to the below. They have their zeros at 0 and a, at 0 and b correspondingly, and of course they have their maximum then in the middle. And it's also not too difficult to compute the value at the maximum. And what about the derivatives? They are concave parabolas, so they have a second. First they have a constant second derivative, as most of the parabolas have, and it's negative. Actually, it's minus 1/2 here. So what does that mean now for not for the discretization, but just for the Laplace equation? If we apply minus the Laplacian to this function, wh1 plus, this is a misprint here, of course. I see this must be a y here. Otherwise, it would not make sense here. I will check where this misprint comes from. So here we get a 1/2. Here we get a 1/2, so we get a 1. The solution is non-negative everywhere, so we have Dirichlet data which are non-negative. So in some sense, this is a super solution in the continuous setting for the problem Poisson equation with f equals to 0 and f equals to 1 and g equals to 0. Now let's see how this continuous super solution transfers to a discrete super solution. That is by just looking at the nodal points of this. So we now make a vector out of this. We just look at this function at the nodal points. But the point is, if you remember the consistency estimate based on the error estimate for the second difference quotient, then we had an h square, and we had then a factor which was some number times the L infinity norm of the fourth derivative, as far as I remember. What is the fourth derivative of a polynomial, of a parabola? 0. What does that mean? What is the error if I have a parabola and I do approximate the second derivative by this difference quotient we are using? What is then the error? 0. It's exact. So there's a certain relationship between the order we have seen in H and the amount of exactness, so to speak, whether this formula is exact only for constants or for linears and so on. We don't want to discuss that now. So that means we can substitute, so to speak, the Laplacian here by the Laplacian H, by our 5-point stencil. So if we now apply our 5-point stencil, that is what is done here, again using the right-hand side 1, then this equation is fulfilled exactly. And as this matrix is positive and this vector is non-negative, then we just have this estimate. So we have fulfilled what we would like to see with this WH. Now we have to estimate the maximum norm of WH. Of course, the maximum norm of the grid function can be estimated by the maximum norm of the full function. And the maximum of the full function we have just seen. We have two parabolas. We have to go to in both directions to the midpoint. And here we have to compute what the value is. And here we get what I already indicated, this 1/16 times a squared plus b squared. Okay. Now let's see what we can do with this consideration in general. And there's a very interesting relation in this. In some sense, we are only looking at a very specific situation. And you can criticize that because eventually you find a lot of situations where this inverse monotonicity does not hold. But if it holds, then things really become more simple. And this we will see in coming to the next theorem. So the way is the question is now how to construct such a sequence WH. And what we did here for this example, we can try to mimic in the general situation, and this I will explain a little bit. So let's assume we are looking at a general boundary value problem. We write it in this abstract form. We have some differential equation, we have some boundary condition. And let's assume that for this that this boundary value problem has a solution for some right-hand sides f and g, where f is greater or equal to 1, and g is greater or equal to 0. And you see, now I have introduced this notion of super solution. It would be also sufficient to have a super solution with this property. And in the special situation of the Laplacian, we have seen that it's quite easy to come to such a super solution. The advantage, of course, of looking at the continuous case is now we have really one function, nothing dependent on h. And the idea is now, as we did it before, to construct on the basis of the super solution W a sequence WH where we can assure that the infinity norm is bounded. What do? We just evaluate at the nodal points, at the grid points, and then, of course, the infinity norm is estimated by the infinity norm of this one function. So if this would really turn out to be also an appropriate choice in the discrete case, this would be just our constant in the estimate. Okay. In principle, we can do this if we have an inverse monotone problem. That is the statement. Of course, that is to be understood not only in the interior, but also correspondingly for the Dirichlet boundary conditions. And that is the assertion which tells us that in principle, at least for small values of h, this is okay. So the situation, what is this? The statement. So we have such a solution, or super solution, as described. We look at a discretization in our general form, which is consistent. That is the assumption. And we need a little bit of a further assumption, which in principle is only of technical nature. We have to assume that from some value h tilde on, so we are speaking about small values of h. Maybe we cannot specify this h tilde. We can only make an asymptotic statement out of that. We are sure that what we have here on the right-hand side, in this construction what we have, we can estimate it from below by a positive constant times the 1 vector. That is not a really terrible assumption, because look at our typical situation. Our typical situation would be that this matrix is greater or equal to 0. This vector is greater or equal to 0. The f, we said, is greater or equal to 0. So we have this under our typical assumptions. We have this for each h tilde and alpha tilde equals to 1. It's only a technical point. And the assertion is then if we are willing to go a little bit below this alpha tilde, for every alpha smaller than alpha tilde, we can find an h, capital H, such then this sequence of vectors we have defined defines this property, which allows us now, together with inverse monotonicity, to conclude the stability. So to put these results together, assume we have proven this, putting these results together means if we have an inverse monotone problem, if we have a consistent discretization, then at least asymptotically for small h is and by this that is what is the important thing for stability, then it's stable. So that is a very nice situation, because stability is really the bad guy, the difficult thing to prove, the analytical part of the thing. The other thing you can leave to Mathematica or whatsoever. To do a consistency order computation, you throw it into Mathematica, it will compute all your Taylor expansions you would like to have, and don't have to think about anything. Stability is the key point. And here, inverse monotonicity gives you stability for free. That is very nice. Okay, the proof is very, very simple. Okay, let's look at this quantity here. What is this? What did I... okay, so what do I do here? I take the W. The WH is, so to speak, the evaluation at the grid points of the exact solution. What do I do here? I plug in the exact solution at the grid points into my discrete problems, where I have to put everything to one side. And now consistency just says this quantity goes to 0. That is the definition of consistency. And maybe with some order, if we have we have an order of estimate, but that's not necessary here. So I know by assumption that the maximum norm of this quantity goes to 0 for h equal to 0. Okay, so let us rewrite this relation in terms of a relation for WH. So this is given here. So what can we do? We can estimate, of course, this quantity from below by minus the maximum norm times 1. This quantity we can estimate by assumption by alpha tilde times 1 for small h. And then you see, if I relax it, this quantity here goes to 0. So if I relax a little bit here, eventually I can assure that I'm still above alpha times 1. That is just convergence, what is used here. Okay, so what is still the problem here? Of course, there's it's not exactly what we would like to have. I missed this remark. Here's an alpha times 1. So it's not the quantity WH, norm of WH, which gives us the constant in the stability estimate, but 1 over alpha times WH, because I've divided number alpha. This is then the quantity which fulfills what I would like to have. Okay, so I still have a few minutes, so I will use these final minutes. I want to finalize this discussion of difference methods today, before we come to the real stuff from next week on. But let me end up with a few remarks on generalizations and variations of the problem. So we could do, basically in this general theory we have now depicted, of course it can be made more general. Also Neumann and mixed boundary conditions are included. With the mixed boundary condition, one has to be a little bit careful. That is similar to this reaction term, which I have discussed. There are, I think, 3 points I wanted to discuss a little bit, maybe at the blackboard. The one is, and to the full extent, I will, let me see, to the full extent, maybe I will only discuss it next semester. But there's one thing we should have a look at it, because it's enormously important in terms of applications. That is what happens if we include first order terms. That is what happens if we include convective terms. Up till now we have only spoken about diffusion. So what about convection? times convection. So to simplify the situation, so we now have a log plus convection. So to simplify the situation a little bit, I look at the following model problem, and I will only discuss the discretization of the PDE. So we do it quite simple. We have minus the Laplacian. To be a little bit more precise, I keep a constant here in front. That would be in the applications the thermal conductivity or whatsoever, or the diffusivity, you name it. And now instead of plus a certain field C times gradient of U. Okay. So now we have to discretize here this guy here. To be more precise, we assume, so what do we have here? We have here a term, of course, C1 times x1 derivative plus C2. If we write it in 2 dimensions, you see we can equally well also have this in 3 dimensions or whatsoever. So what do we have to discretize the first derivative? We discussed this already, and we came to the conclusion that the central difference quotient maybe is a good solution because it preserves our order of consistency. What does that mean for the matrix? Let's assume we have the lexicographic ordering. And look at this term here. What entries do we get in this term? So we get a C1 over H at the diagonal. Sorry. We get nothing at the diagonal. And then we get a C1 over H over 2H, stepping 1 in the plus direction, and we get a minus C1 over 2H stepping in the other direction. You agree? So now we add what we have from the diffusive part. So this is only x direction. You have the same thing for the y direction. That will turn out exactly the same thing. So now what do I have here in the central point for the, what do we have here? K times I guess 4 over h squared. And then we have here minus k over h squared. And then we have minus k over h squared. Now let's think about our properties. Is this good or is this bad for our properties? So at the diagonal element, we haven't changed anything. No problem with the sign condition. What about the sign condition here? Yeah, let's fix. We have to speak about a situation. We assume that the C1 is greater than 0. Can also discuss the other case. Okay or not okay? What was the sign requirement? It has to be negative. It has to be negative, non-positive, and there's no problem here. Minus, minus. What about here? There's a problem. Our requirement would be less or equal to 0. What does that mean? That would mean, let's do a small computation. We multiply by, say, h squared and 2. Then we have here C1 times h less or equal to 2k as far as I see. Okay, let's bring the k to the other side. Then we have this requirement. That means we have the discretization parameter, and here we have a quantity which reflects the relation of diffusion and convection, and this product has to be bounded by a specific number. And now you see where the problems come from. Let's assume that this quantity is 10 to the minus 6 here. 10 to the 6. That's not very unreasonable. That would mean for stability, and we get our stability via inverse monotonicity. For stability, we are forced to compute with step sizes less to 10 to the minus 6 times 2. For accuracy, maybe it would be enough 10 to the minus 2 or 10 to the minus 3, but stability forces us to do an extremely small step size here. And to do this a little bit more precisely, whom of you knows the word Peclet number? None? Knows a little bit of fluid dynamics? So there is a dimensionless number. This is called the Peclet number. For some strange reason, it's written in this form. Of course, that's ridiculous to note a number by 2 letters, but it is the case. And the Peclet number basically is something which characterizes the strength of the enforcing flow field over the quantity which characterizes the diffusive processes. That means if the advective process dominate, the Peclet, and this is now a dimension, this number has a dimension, and to make it dimensionless, we have to multiply with a length, and one often uses the diameter of the domain or something, some length. This is now dimensionless, and if at or con, up to you how you want to call this, convection dominates diffusion, this just means that the Peclet number is a very large number. The Peclet number is a number of the problem. The problem is convection dominated or it is not. So what would our requirement? Our stability, our requirement, so we can fix it, put it in this word. There are some further points to discuss, but I only look at the sign conditions right now. I have no time for anything else. Requirement for inverse monotonicity. Monotonicity would be, if I take this and this, would be Peclet number times the diameter of the domain is less times h is less or equal to 2. So that really means a strong smallness requirement on the h. Okay. What about one-sided difference quotient? We know actually we do not like to do that because we will lose the consistency, and by that we will lose the order of convergence. But maybe in terms of the qualitative properties of the solutions, we are forced to do it. We just continue with these situations C1 greater or equal to 0. And let's try, what does that mean? That means in the x direction the flow comes from the left. And convection is a directed process. That's, yeah, it just takes the particles and takes it with us. So it does not make sense. Diffusion is an indirected process coming from Brownian motion. It doesn't make sense. It makes sense to take central difference quotients for diffusion, but in some sense it is unphysical to take central difference quotients for convective processes, because that means you take already information from a point where the flow has not yet been with this particle. So what does that mean by this? What are we tempted to now to use? Would we like to use the forward difference quotient or the backward difference quotient in this situation of the flow going from left to the right? You decide, forward or backward? You choose backward. Okay, so we do backward. Okay, doing backward difference quotient, what does that mean for our now here the same thing. Of course, these terms, they do not change. I missed the k here. K 1 over h square. K 1 over h square. So we go backwards. So we have a positive contribution here. Where is it? That is the wrong page. I think I should be also able to do it without my notes. We have a positive contribution here, so we get the plus C1 over 2h here, the diagonal. That is not bad, because it improves, so to speak, the positivity in the diagonal. And the minus quantity we get here. Okay, and this is good. Now we preserve the sign conditions without any requirements on the smallness of the h. But of course, we have lost the second order. And what we have done, maybe that should be my last remark then. The other two subjects, maybe I come up next time or I skip them. What we have done here, in fact, you can see if you look at the following computation. So we use the, how do we know that? It doesn't matter. So we use the backward difference quotient. Let's look only at the x direction as we did it. So we use this guy here. But we have the following identity. I just write it down, and then you can check that it's true. I have here a certain factor depending on h, and now I write down what I really want to have, namely the central difference quotient minus, that is now only in one direction, therefore there's only a 2 here. That is what I really want to have. Of course, I don't have a sorry. Forget it, what I said. What I really want to have is this guy here. I want to have the central difference quotient. ux plus h y minus ux minus h y over 2h. Of course, this is not equal to this. I need a correction term. I have to figure out what the difference is. This is the correction term. But what is the correction term? The correction term is just a second order difference quotient, but multiplied with a quantity depending on h. So what do? We, so to speak, change our problem. We add some diffusion, but not a fixed diffusion, because that would change the problem at all. We add a diffusion which is dependent on the discretization. And in this sense, we can interpret what we are doing is we use the central difference quotient, but we add a diffusional term depending on the discretization. Therefore, this upwind scheme, what we are doing, this is also called the upwind scheme, the full upwind scheme. We are always going back in the direction of the flow. If the C1 would be negative, we would have used a forward difference quotient. This is you can interpret as a scheme with artificial diffusion, artificial viscosity, which is added here. Okay, let's stop here.